Yes. Hi. My name is Justinas. I am from DTU. My two PhD supervisors are Peder Bakker here in the back and also Henrik Madsen. I think some of you have met them. And I'm also at the at-scale gang of a person, right? And I come here with a background in applied statistics. So I'm very much not a building engineer. I'm going to talk to you about what we call the X-ray solution, which is our kind of first at-scale solution of digital building energy performance certification kind of thing. And so just to set the scene a bit, like some of you have attended the summer school that Peter and Henrik organized, and you've seen that we have a lot of different methodologies, a lot of different models, a lot of different possible solutions. And so what we're building is a toolbox, right? Because like Henrik likes to say, no model is correct. Some models are useful. So we really need to know when to use the correct tool for what job, right? And as our French colleagues have pointed out, I'm also really keen on uncertainty quantification. So let's dive into it. So right now, the EPC, right? It looks something like this in kind of a lot of different European countries. It's all a little bit different, right? But we have some standard values, we have some normal energy consumption calculation, right? And then we calculate some EPC. And as we have seen, I'm not going to reiterate what we've seen a lot. Different buildings are different, basically, right? So no single approach fits everyone. But we can change this now because, so at least in Scandinavia, and particularly in Denmark, we have smart meter penetration for electricity meters. It's around 100%. And then for district heating, it's following quite closely by. And what we have is Center Denmark, which is our data platform nonprofit owned by all the different energy providers in Denmark, where they're building a data platform to collect all their data together. So I live in relative data heaven compared to most of you. So now we can leverage this big data to look at some actionable results. So like a small little overview, that's like there's something weird we found just by looking at some single family homes. And we've seen this kind of on different data sets, but I'm just showing one from like Fredericia, that's where the Center Denmark is, so that's why. So we have EPC labels on the top range of A2010 to A2020. And what we see is that actually A2010 labels buildings outperformed the A2020 and A2015 usually, which is weird, right? So what happened with this new building regulation, which change every 5 years, that the newer buildings underperform? Well, that's a great question. I'm not a building engineer, so I can't answer that. But the goal with this kind of extra solution is, so we have 3 focus areas, right? It's like, okay, one, we need something that is like physically realistic. We can't just live in the sky and not just say, my model predicts good, so it's a good model. No. We need something that is based in reality. Second, it has to be robust. We're going to be applying this on, 100,000 buildings, right? If we were looking at a town scale, right? So it has to be generalizable for residential and non-residential buildings. And lastly, and most importantly, okay, we need to quantify the uncertainty. We need to be able to stand behind our results. And what happened is that when I took over this kind of project, we applied some models on about 20,000 buildings. And then they were offered mortgages to repair the buildings, but there was like no validation of results, no kind of clear quantification of uncertainty. And I was like, okay, bro, bank gets to give out a mortgage, so project is a success. But realistically, I don't know. They didn't check if the renovation made an impact, so I was very upset about that. Anyway, so I addressed the 3 focus areas with like 3 different approaches. So we go back to basics. We have many different solutions, but okay, energy signature is pretty all right. Like it's a good place to start, and we can build on top of this. And then we will, it's maybe a bit too basic, so we need to add some time series analysis and also add some Bayesian statistics to really directly quantify uncertainty. Let's see. And so the main direct outputs of this kind of extra solution is that, we have accurate forecasts. That's, not so interesting. We have the R square of like 0.94. Okay, whatever. But then we also have some building parameter estimates, for which we have kind of posterior probability distributions of how likely we believe they are and how likely, according to this model, they would recreate the data we're seeing. And so we can estimate, of course, the heat transfer coefficient. We can estimate the wind penetration, solar gain factor, maybe some inhabitants impacts, right? Especially on apartment buildings where we have like daily, weekly variation, things like that. And so these are the main outputs, right? But kind of the reason we start with the energy signature is because a lot of you are familiar with building physics, which lives kind of on this side of the board. But we can actually show on paper that we can go from energy signature extended to with some autoregressive coefficients, moving average coefficients, that then it becomes like a discrete type approximation of this kind of building physics envelope models, right, that you have encountered. So the question is, when we're running this on 100,000 buildings, and maybe we can't have a model running for 40 seconds to fit one model, where do we cut? Where do we, where is this diminishing returns and what do we want? And that's where the understanding what models and what methodologies provide what really comes into play. So right now we're kind of playing around in this area because it's a good mix of being tied to some physical reality compared to, like, you know, differential equation models, right? And it's simple enough where we can fit it easily and add Bayesian statistics to it. So the results from that, okay, of course, like I mentioned, we can have your heat transfer coefficient, you can have some, okay, uncertainty quantification, and then so for heat transfer coefficient, you don't just get a single value and like a little confidence interval around it. Okay, this will maximize my predictions. No, you get like a probability distribution around your estimate, and okay, according to this model, it should be somewhere in this range, right? And then that makes it a lot more interesting to evaluate and compare to the, for instance, energy performance certification data in Denmark. And then, of course, yeah, we can start examining the building stock. So, you know, one very unsurprising result that we can hear echoed today is that, okay, if we compare the nominal energy consumption that is predicted with the EPC value versus the actual energy performance, when we, okay, transfer the building with the model into the reference climate, we can see that the worst labeled buildings, D, E, F, G, perform way better. Okay, this is the difference between the labels, basically. We can see that the worst buildings overperform and the best buildings underperform significantly. It's okay, I have 2 slides, so it's no problem. And so the immediate kind of results that we're working on implementing now is, okay, we can identify low-hanging fruits. We can ingest 100,000 buildings, run the models for like a day, and then we can find, comparing to the peers in the same data set, where are the low-hanging fruits of your renovation objects, right? So we can answer different, we can address different stakeholders in this whole system, and one, first, better allow the building owners to understand their buildings. 2, also, when we evaluate buildings en masse, we can decompose the energy consumption in this kind of building population by, okay, is it temperature dependent? Is it wind dependent? Okay, how much do we get from the sun, right? And we can also indicate to the market, hey, what do we need? Do we need a lot of new insulation? Do we need a lot of new buildings? Do we need PV? Do we need to just control the system better through flexibility and dynamics in the system? And so, yeah, and then of course we can give individual buildings some suggestions. Okay, your building looks pretty good for comparing to all your peers, which is a nice thing to know for people. Because when you have data on a whole population, right, we can start comparing and you can see how things compare. So I think that's kind of everything I wanted to say, and I think I'm right on time. Perfect. But yeah, thank you for listening. And I don't think I have anything else to mention.